Hello and welcome to the demonstration of TPV, a lightweight analysis tool for validating temporal properties of UML class diagrams. Within the context of model-driven engineering, software designers use the unified modeling language to create application design models. These models are then used to drive the software development process, leading to the development of production software. UML models can be checked for correctness using model checking, a prominent approach used in the industry for verifying that a model of a system satisfies its behavioral requirements before it is used for system development. Despite recent advances, researchers have argued that current UML-based model checking tools exhibit problems in their usability, effectiveness, and efficiency. Therefore, we have created a UML-based analysis tool that is tailored towards UML designers. We call this tool the Temporal Property Validator, or TPV for short. TPV features a specification technique that streamlines the specification of complex temporal properties, a lightweight analysis technique that strictly uses UML-based tools and notations, and an optimization technique that reduces the search space for analysis. We created TPV as a plugin for the UML-based specification environment. Users must provide two inputs to analyze a system using TPV. First, an application design model, augmented with specification of operation behavior in the form of OCL pre- and post-conditions that models the structure and behavior of the system. The second input is a behavioral requirement for the system expressed as a temporal property in TOCL, an extension of OCL for temporal property specification. TPV then checks the behavior of the input model and may or may not produce a counterexample within the given analysis configuration. To install TPV, simply download the tool files we have provided and place them in the desired directory. To launch the tool, open the bin folder and run the use executable appropriate for your system. Now, we will demonstrate TPV. We will first specify a simple class diagram within the UML-based specification environment. This class diagram models a traffic light system in which a button can request that a traffic light switch the state of its car and pedestrian lights. Once we are finished writing our model specification, we can save it to a file with a .use extension. We can then open the file by going to the File menu and selecting Open Specification. This model specification will be the first input for TPV. To validate the traffic light model, we open the TPV analysis plugin. First, we select the file containing the class diagram specification that we will analyze. Then, we input a TOCL property for analysis. This can be done by selecting an existing file containing a specified property or by specifying a property within the plugin interface. Users can write TOCL constraints from scratch in this dialog box, or they can use a set of temporal specification pattern templates that we have included in TPV. These pattern templates can facilitate the specification of complex temporal properties. Here, we use the response pattern to specify a system property that states that when a traffic light is requested to change, it will eventually switch its car light to red. Users can then choose to apply an optimization technique. We can now begin the validation process. TPV implements a lightweight approach to checking system properties that only considers a subset of the possible execution scenarios. In addition to the optimization technique, we use two methods to restrict the search space: search scope and search depth. Search scope defines the number of objects of each class that can exist in one system snapshot, while search depth specifies the number of transitions to be considered for analysis. This is a counterexample produced by TPV in which the property we defined is violated. For complex analyses, counterexamples can be complicated and hard to comprehend. To understand the counterexample scenario more easily, we can view the scenario as a UML sequence diagram. Once users have a general understanding of the overall execution, they can explore the counterexample in more detail. The reason this scenario is a counterexample is that there exists a traffic light object that has been requested to change in one system state, but has not switched its car light to red in the following state. In this case, TPV has found a counterexample within a small search scope. However, if TPV does not find a counterexample in the given search scope and depth, we can increase the scope and depth and redo the analysis, increasing the confidence that a counterexample cannot be produced by the model. That is all for our demonstration. Thank you.